We're going to talk about two more kinds of reactions. The first is an acid-base reaction. This is also called a neutralization reaction because we have an acid and a base, and when they mix together, they neutralize each other. The other one we'll talk about after this is called a gas evolution reaction, in which a gas is produced. Reactions, chemical reactions, can belong to more than one category. You can be an acid-base reaction and a gas evolution reaction at the same time. So before we talk about acid-base reactions, we have to talk very briefly about what are acids and what are bases. The Arrhenius definition of an acid is it is a substance that produces hydrogen ion in aqueous solution. This matches what we learned about in nomenclature. Acids are molecular compounds that form hydrogen ions when they're dissolved in water. So an example here, HCl. We should recognize this as an acid because it starts with H. When this dissolves in water, it forms hydrogen ions and chloride ions. Now let's think about this hydrogen ion. A hydrogen ion came from a hydrogen atom, right? How many protons does a hydrogen atom have? One. How many electrons? One. Okay. So if it becomes a plus one ion, that means it lost one electron. So what's left? It is just a proton. We talked about the relative sizes of like the nucleus and the atom, and we learned that the nucleus is like way, way, way smaller than the atom. So here we have the smallest atom, and we've taken off all the outside part, and we just hit the little teeny tiny inside part. Protons actually don't just float around in solution by themselves. I think of them as being like newborn babies. You ever see a newborn baby just, strolling down the sidewalk? No, because they can't walk. And nobody just leaves them out there either, right? Because who would do that? Who would be such a monster, right? You have to take care of them. And if you can't, then you pass them off to somebody. So hydrogen ions are always getting passed off from one person to another like a tiny baby. So this guy's too small to be outside by himself. So what happens is this hydrogen ion is going to get carried by a water molecule. This is an aqueous solution. There's water molecules everywhere, right? Tons and tons of them, right? So this hydrogen ion, which is just a proton, is going to hang out with this water molecule. And when that happens, we get something called H3O+. It's a polyatomic ion, and it has the name hydronium ion. So here we have some water molecules, right? And here's the hydronium ion. It's a water molecule that has an extra hydrogen ion and overall a positive charge. Now, we don't do this to be confusing, but we will often use H plus and H3O plus interchangeably. We understand, though, that hydrogen ions are not out by themselves. They're always going to be with someone. So here, the hydrogen ion was with chloride. When these separate, this guy has to go to somebody else, and so water is going to carry him around. We don't always use H3O plus because it makes writing all the chemical equations more complicated. And so we often just call it H plus, but we have to understand, well, of course, hydrogen's too small to be out by himself. He's going to be accompanied by someone, right? So that hydrogen ion on the acid is called an ionizable proton, because when you ionize it, it becomes just a proton. And so polyprotic acids are many proton acids. They have many hydrogens, and so they have more than one ionizable hydrogen. An example is sulfuric acid. This is H2SO4. There are two ionizable hydrogens here. When you have acids like that, they don't lose all their hydrogens at once. They lose one first, and then they give up the second one. So this one is a diprotic acid because it has two protons. The Arrhenius definition of a base is a substance that produces hydroxide ions in aqueous solution. Most of the ones we're going to encounter in Chem 1A are metal hydroxides, like sodium hydroxide. This is an ionic compound. It dissociates into sodium ions and hydroxide ions when it's dissolved in water. There are other bases that do not contain hydroxide ions. The only one you need to be aware of is ammonia. So what happens with ammonia, when you put ammonia into water, what's going to happen is that it's going to take a hydrogen ion from a water molecule and become NH4+, ammonium ion, and then what's left is hydroxide ion. So even though NH3 doesn't have OH in its formula, it forms hydroxide ion. It's a base because it'll pull a proton off of a water molecule. There are some bases that can produce 2 moles of hydroxide, and those would be things like strontium hydroxide, where when this separates into ions, you've got 1 strontium and you get 2 hydroxide ions. There's no special name for that, like diprotic acid. It's just a base that produces twice as much hydroxide. I don't know. We just don't even call it anything. So when an acid and a base react, the acid is forming hydrogen ions, the base is forming hydroxide ions. The hydrogen ions and the hydroxide ions are going to react together and form a water molecule. And that's where we have the neutralization. So here we have the acid. This is going to form hydrogen ions and chloride ions in solution. This hydrogen ion is going to get together with the hydroxide ion from here and form a water molecule. So we've got the hydrogen ion and the hydroxide ion, and they're going to make water. Of course, what we really have going on in solution is that hydrogen ion is not out all by himself. It's being carried by a water molecule. So you can think of water as the babysitter, hydrogen is the acid, and so this babysitter is tired of hanging on to him, and so it's going to pass him off to hydroxide, which is remarkably like the original parent, right? Where did this hydrogen ion come from? Well, ultimately it came from a water molecule. And so the hydronium ion gives its extra proton to hydroxide, which is missing a proton, and then we have 2 water molecules. Any questions? Here we've got our HCl and our sodium hydroxide. So here's that H3O plus the hydronium ion. That's the hydrogen ion from the acid. And that's going to combine with the hydroxide ions from the base. And then we're not going to show them over here because they're just part of the solution now. So here's where they finally tell you what the strong acids are. There's these guys. Those are strong acids. All other acids are considered weak, meaning that they do not ionize completely. And the bases, any of these metal hydroxides are all considered strong bases. The only weak base you need to be aware of is ammonia. So we need to be able to write equations for acid-base reactions. And we're going to use the same strategy we did for the precipitation reactions. Look at the ions in the reactants, swap the partners, and put them together to make the products. So here, write a molecular equation and a net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So we're given the reactants, HBr and LiOH, and we need to predict the products. This is an acid it's going to form hydrogen ion and bromide ion in solution. This is a soluble ionic compound, right? That's going to form, it's a base, it's going to form lithium ions and hydroxide ions. And so we're going to swap partners. This is the party in a beaker. And I'm going to put H plus and OH minus with each other, see how they like each other, and LA plus, Li plus, and Br minus. Well, if I just put those two together as an ionic compound, I'm going to get HOH. How'd you pronounce that? Ha. You can't do that, no. It looks weird, huh? You look at that and you go, huh? That's not right. Yeah, that's not right. That's H2O. Okay, so if you write HOH and it looks weird, you're right, it is weird. Erase it and write H2O. Is water aqueous? It's a liquid. Because how can water be dissolved in itself? And then these guys, well, how do we put those two together? We got plus one and minus one, so we're going to have LiBr, and then we ask ourselves, is that soluble? Gotta look at the chart. The first row of the chart, ammonium, lithium, sodium, yeah, it is. So this is soluble. So there's the molecular equation. We could identify that as me, molecular equation. Now I've got these kind of scribbles down here. They're not asking me for the complete ionic equation. Maybe I feel like I need to write it out anyway, but maybe I don't. We can kind of make this into the complete ionic equation. So this is an acid, and this is a clue here, strong acid. This is a strong acid. Do we separate a strong acid into ions? Yeah, we do. So those are going to be separate ions, so that's H plus and Br minus. This is an ionic compound that's soluble. Do we separate that into ions? Yes, we do. So I've got lithium and hydroxide. And then over here, do I separate water into ions? No. That needs to be written together because that's a liquid. It's not aqueous. And then we've got this also a soluble ionic compound. So there I kind of turned my little scribbles into a complete ionic equation. So what things didn't change? The lithium is the same on both sides. And the bromine. Those didn't get involved. So I'm going to copy down what's left, putting the state symbols back in. H plus, OH minus, making H2O liquid. And that would be the net ionic equation. That is the net ionic equation for a lot of acid-base reactions. And the balances say moo. Does it sound like cows? Maybe it's just because I grew up in Iowa. Yeah. They're calibrating themselves. I don't know why they have to do that, but any questions? Let's do another one. This one is a weak acid. So we've got aqueous HCHO2, which probably looks unfamiliar to you because there's no reason it should be familiar. HCHO2, we're told that it's aqueous, and that's reacting with aqueous sodium hydroxide. And they want the net ionic equation. Well, we're going to look at the partners to predict the products, right? So this is an acid. We should recognize that because it starts with H. I don't expect you to know what its name is or be friends with it or anything, but we're going to take the H off, and everything that's left there, CHO2, is going to be the other anion, right? So I'm going to have H plus, and I'm going to have CHO2. And then this guy, I'm going to have sodium ions and hydroxide ions. To predict the products, we have to separate them into ions and then put them back with different partners. So H plus and OH minus, and we've got sodium plus and CHO2 minus. So what does H and OH make? Water. And this is going to be an ionic compound, right? Is it going to be soluble? Ammonium, lithium, sodium, potassium, always soluble. So that's going to be soluble. They're not asking us for the molecular equation, so we don't actually have to write it. Let's not. We want the net ionic equation. So we kind of have to think about a complete ionic equation. So HCHO2, should that be separated into ions for the ionic equations? What kind of an acid is it? It's a weak acid. A weak acid means it only ionizes a little tiny bit. Most of it's intact molecules. So in the ionic equations, we're going to show things like they mostly are. And so that would be shown as being together. This is aqueous. This is an ionic compound. That'll be shown separately.
So only just make sure strong acids break down weak acids do not.
Correct. Yeah. Water. Well, that's not something that's separated into ions because it's not aqueous. And how about this guy? That's aqueous and ionic. So that would be separated into ions. So now we're going to look and see who didn't get involved. Well, there aren't as many things now, right? But let's look at sodium. Sodium came with just, a friend, and he's going to leave with a different friend. So sodium didn't get involved. But I can't cancel this out because that is a molecular, it's a weak acid, and so it's mostly there as molecules. I guess you could say that a weak acid is a couple that comes to the party and they don't mix very much. They don't, it's like, well, I'm going to run off to the bathroom real quick, but then I'm going to come stand right next to you again. Of course, in that instant, right, that she leaves, he sees hydroxide and boom, it's all over. So, I don't know. Analogies go some strange places sometimes. That is a new direction I haven't had before. So we're going to write down what's left. This is the net ionic equation. Sodium is not going to get shown here because what if hydroxide had brought potassium instead? The same chemical reaction would have occurred. Or ammonia, right? Same thing would have happened. It doesn't matter who that was. They didn't get involved. Any questions? Right, we didn't break this one down because it's a weak acid. And weak acids are the only aqueous things you don't break down. So, you know, if you're one of those people who are like, I don't have time to learn all of this stuff, right? Well, most of the time, break all the aqueous things down and none of the rest of them, and you'll be okay. But once in a while, when there's a weak acid, then you won't be okay. Which brings us to titration. So titration is an experimental technique where we take a solution that we know the concentration of, and we react it with a solution that we don't know the concentration of, and using stoichiometry we can calculate the concentration of the unknown solution. And we'll be doing this at least 3 times in lab. So you add the one solution to the other until the reactants are in just the right ratio. It's called the stoichiometric ratio, and that's called the equivalence point. The trick is, how do you know when you get to the equivalence point? Because normally there's nothing you can see or detect. Well, in acid-base titrations, we generally use an indicator. So an indicator is a compound that changes color when the solution undergoes a big change in pH. Like when it goes from acidic to basic or from basic to acidic, that will change color. It's very intensely colored, so you only need a little tiny bit of it. So when that indicator changes color, we know that we're at the equivalence point, and we have the moles of hydrogen ion are equal to the moles of hydroxide ion. Pictures. So illustration, so this is what we use the burettes for. So here, putting sodium hydroxide in the burette, and maybe you have hydrochloric acid in the flask. We know the concentration of the sodium hydroxide, and we're going to add sodium hydroxide to the acid until the indicator changes color. And that tells us to stop. You've added enough sodium hydroxide. We can look at the difference in the level of the burette and identify how many milliliters of sodium hydroxide have been added. And we know the concentration, so we can find out the moles. Then we're going to be able to look at the chemical equation for this reaction and see what the mole ratio is. And we can calculate the moles of hydrogen ion. And then knowing the volume of the acid that we started with, we can calculate the concentration. This is what it looks like when you are actually doing it. It looks like you're adding water to water. And then after a while, adding to water to water makes it start to turn pink. And you're like, wow, this is like magic, right? So you add a few drops and it turns pink in the middle, but if you mix it, it goes away again. It's turning pink here because it's a little bit concentrated in base, but then as soon as you mix it, it neutralizes it. And then at the end, 1 drop or even less than a drop will make the whole solution turn pink. That's the equivalence point. Technically the end point, but yeah, basically the same thing. So titration calculations are an important part of chemistry. This is a solution stoichiometry problem, which we've already learned how to do. Titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution. To reach the equivalence point, what is the concentration of the unknown H2SO4 solution? This is not a dilution problem, right? We don't see the word dilution. We don't hear anything about the solution with an initial concentration or a final concentration. This is a chemical reaction, right? We have 2 different substances that are reacting with each other. So we need a chemical equation. So we've got H2SO4 and we've got KOH. Like on an exam, the balanced chemical equation will be given to you, but we're using this as an example to do another acid-base equation. So we've got H2SO4 and KOH.
Does it matter the order the molecules?
It does not matter the order. That's a great question. You can put the KOH first and then the H2SO4. It's the same thing. So these are going to react. the acid, the hydrogen ions from the acid are going to neutralize the hydroxide ions from the base. So let's look at this. Sulfuric acid has 2 hydrogen ions, right? And a sulfate ion. And KOH has a potassium ion and a hydroxide ion. And we're predicting the products the same way we did with the precipitation reaction, swap the partners. So put H with OH and K with SO4. So here's my H plus and my OH, and what does that make? Water. And then I've got K plus and SO4, 2 minus, and what compound would that make? Has to be neutral. If I put one of each of these, I'm not going to have a neutral compound. It needs to be K2. So K2 SO4. And then we need to balance it. This is one where starting at the beginning might take longer, and we don't have a lot of time, so I'm going to start in the middle because I know it's going to go faster. Let's start with potassium, just because I said so. There's 1 potassium on the left side, and there's 2 potassiums on the right side. So if I put a 2 in front of KOH, my potassiums are balanced. I have sulfate on this side and sulfate on that side, 1 of each. Right? And then what else do I have? I have OH minus here. Let's do this. So I decided there were 2 of those, so that's 2 KOHs, right? And that's H plus. So these guys are making that one guy at the end, right? And so that makes one water molecule, and this makes a second water molecule. So there's actually 2 of these guys. Here, the acid is a polyprotic acid, H2. That tells me I need to balance this. It's not going to just be a 1-to-1. Let's see if I can erase this because I need this space now for something else. So now I came up with my balanced chemical equation. Now I'm going to take the numbers that were given to me, 20 milliliters of sulfuric acid, 22.87 of KOH, and they're asking me for the concentration of the H2SO4. I'm going to write these numbers under the formulas in the equation. And they're asking me what the concentration is. So that's going to end up being moles per liter. So stoichiometry, grams to moles to grams. The H2SO4 is the question thing. That's not what we're starting with. The KOH, we have more information about. That's what we're starting with. Do we have a mass of KOH or volume? We've got a volume. So we're not starting with grams, we're starting with volume. And then at the end, we need to calculate the mass of H2SO4. We want the concentration in moles per liter. So, I'm like, well, wait a minute, what do we do with this? Well, what's molarity? Moles over liters, right? Molarity equals moles over liters. So to find the molarity, I need the moles of sulfuric acid and its volume. They gave me the volume right here. If I stop at moles of sulfuric acid, I just need to divide. I need to put that in here and divide. And so we don't need to do that last step either. So you start with grams to moles to grams, and then you look at what you've got and what it's asking you for, because there's like so many variations. Like that problem on the worksheet with limiting reactant, and LiOH and Li2CO3, and everybody was like, what the heck? Right? That was just the mole in the middle part. It was supposed to be simpler, but then people like, I don't know. It's not what you were expecting, right? So then it becomes hard. So we need to get used to this, that things are going to come at us a little differently. So I'm going to start with my volume. So I have 22.87 milliliters of KOH. And then I'm going to convert to moles of KOH. And then I'm going to convert to moles of H2SO4. And then actually I'm going to stop because I want moles of H2SO4. Well, normally we would have liters down here, right? Because that's the molarity is moles per liter. But this is milliliter. So we can pull that little trick again and say, well, milli stands for times 10 to the minus 3. So I'm going to write that instead of milli, and then I don't really have to convert. So now the liters cancel. And down here, moles of KOH, and those are going to cancel. So this is the molarity of the KOH, which they gave me, 0.158 moles per liter. Moles to moles, that's the mole ratio from the chemical equation. There's 1 mole of sulfuric acid for every 2 moles of KOH. 1 mole of H2SO4 for every 2 moles of KOH. So 22.87 times 10 to the minus 3 times 0.158 divided by 2. 0.0018067 moles of H2SO4. I could go on and find the grams, but that's not going to be useful. So I'm finding the molarity, so I just found the moles. And then I need to divide by the volume in liters. Well, it was 20 milliliters. So 20.0 milliliters, but I want that to be in liters. So I can do that thing again where instead of writing milli, I write what it means. So 0.0903 moles per liter, which is the same as 0.0903 capital M. Questions?